Last step, catalysts. What is a catalyst? Well, a catalyst is going to be a substance that affects the rate of the reaction without being in an overall reaction shown. So a catalyst is going to be consumed and then produced in a reaction. Most of the time, students get catalysts confused with intermediates. They are not intermediates. And so we're going to take some time to observe what is a catalyst and how can we identify it. Catalysts work by providing an alternative mechanism. So they change the overall reaction. And what that does is effectively lower the activation energy, and therefore they speed up the reaction. So if you've heard a catalyst speeds up a reaction, how they do that is by providing an alternate mechanism. One of the most prevalent examples that I love to talk about is ozone depletion. Now, in our atmosphere, this reaction of O3 reacting with oxygen atom, yes, oxygen atom does exist. It's just not the most prevalent one in our atmosphere. It produces 2 oxygen gas molecules. This is a very slow reaction, and actually there is a equilibrium with the reverse. All right, that reaction is very important. What it needs is sunlight. Remember, E equals H nu, E equals H, Planck's constant, times frequency. Oxygen and oxygen atom and ozone can react by absorbing the harmful UV rays from the sun to produce oxygen gas. And then going backwards, what actually happens is heat is released. Instead of very, very bad UV rays, we get to be warm and nice and fuzzy and have the perfect temperature to support life on Earth. Now, this reaction is very, very important to us. We need the ozone to be able to interconvert in this reaction forward and backwards. It is very slow, but it is very protective. Now, in the mid-70s, a lot of new molecules were being produced that contained halogens. They were called chlorofluorocarbons, small carbon chains with a lot of halogens on them. And what they were used for, the biggest one that I can tell you is spray cans. This could be anywhere from paint all the way to hairspray. And they were used to pressurize. And so what happened was they weren't harmful necessarily to us, but the chlorine in those molecules, the chlorine atoms would pop off and then go up into the atmosphere. And in the upper atmosphere, they actually catalyze the forward reaction of the ozone depletion. They make it go through a different mechanism. That chlorine atom reacts with ozone to make O2 and ClO. And then that ClO reacts with the oxygen atom to make another O2 and Cl atom again. So let's look and see, can I add this up? Cl atom and Cl atom, ClO and ClO, O3 plus O2 yields 2 oxygen diatomics. Yes, it's the same mechanism or same overall reaction, but a different mechanism. Happens in 2 steps. Now let's look and see, what did we cancel out here? ClO is produced in the first step and used in the second. That means it is an intermediate. Take a minute. Look at what you think the catalyst would be. Chlorine atom is used in the first step and produced in the second. This is a catalyst. All right, because it is used early on and then remade at the end, it's not an intermediate. It's not in the middle. It's at the bookends. It is driving the reaction to start and it is finishing it at the end. That is a catalyst, very different from an intermediate. What the problem with this is in chlorofluorocarbons in the atmosphere is that the forward reaction, the depletion of ozone, is sped up, and the reformation of ozone from oxygen diatomic is not catalyzed. And so that continues to be very, very slow. So we're having an imbalance of our ozone in the atmosphere. Factors that can affect a catalyst. The catalysts are substances that affect the speed of the reaction without being consumed. And so what most catalysts are used to do is to actually speed up a reaction, be positive catalysts. Catalysts can be used to slow down a reaction. They're called negative catalysts. And there are some, and I will explain one at least that you will see in organic chemistry as well, that would be a slower downer of a reaction. Most catalysts do this though. Here's the overall reaction of ozone and oxygen atom with a catalyst like chlorine atom. What we saw in the mechanism on the previous slide, there are now two transition states, two steps, and overall the activation energy is much lower. A catalyst can be a homogeneous catalyst. All the species is present in the same phase, which is like the previous mechanism we did, where all of them were in the gas phase. A heterogeneous catalyst, species present in different phases, solid, liquids, or gases. Those are also important. More likely seen in organic chemistry though. Catalysts generally speed a reaction up. They give reactant molecules a different pathway though. So they're not providing activation energy. They actually change the overall reaction. And so they change the activation energy. A heterogeneous catalyst hold on to one reactant molecule in a proper orientation for a reaction to occur. And then the collision can take place. Sometimes it also helps start breaking the bonds. We see these a lot with enzymes. And a homogeneous catalyst is one that actually reacts with the reactant molecules to form a more stable, like the chlorine in ozone depletion. An example of a heterogeneous catalyst is in this reaction where we have a carbon-carbon double bond that is gaining two hydrogens to become a carbon single bond. So just to show you what the reactant looks like, we'll have a carbon-carbon double bond, and H2 diatomic is actually going to react. And what catalyst we actually use is a palladium on carbon catalyst. It's a sheet, it's a solid. Ethene is a gas, H2 is a gas, and so this heterogeneous catalyst is a solid. And so what happens is actual absorption and diffusion. The atoms of hydrogen are broken up. Notice we have one atom here, another atom here. So we're actually breaking up the H2 bond itself first. And then we start to get the reaction. And typically one hydrogen atom is added at a time, but it's typically added in such a way that it looks almost identical, right? And then desorption happens where the C now gains the H on either side, and the double bond is now a single bond, all right? And so there's the product. Enzymes are our biological catalysts. Because many of the molecules are large and complex, most biological reactions require a catalyst to proceed at any reasonable rate. Protein molecules that catalyze biological reactions are called enzymes. Enzymes work by absorbing the substrate reactant onto an active site that orients the substrate for a reaction, because most biological molecules are extremely complex. So if we didn't have enzymes to help them orient themselves in the right way, we probably wouldn't be walking and talking right now, would we? And so technically what happens is a very, very fast first step where an enzyme and a substrate connect, and then that enzyme somehow creates the product from the substrate. And the enzyme reforms so that it can be reused again. Typical lock and key mechanism is what we talk about. So we can see that purple substrate attach onto an active site of an enzyme, and the enzyme substrate complex then somehow does the reaction to keep going. Hydrolysis of sucrose is an important one. The bond to be broken is this carbon-oxygen bond right here, connecting glucose and fructose. And so the enzyme can actually start to weaken the bond. The sucrase enzyme can start to pull apart those two and weaken the bond itself. All right.